Hi everyone, welcome to tutorial 46 of our Introductory Python for Image Processing tutorial series. In this tutorial, I'm going to talk about image registration libraries in Python. And there are many of them, so I'm going to just talk about a couple, but then go ahead and Google search if you think these 2 or 3 that I'm going to talk about are not going to be sufficient for you. But I hope you'll find these to be useful for your job. Now, first, let's establish the need for image registration. And this video doesn't seem to work, but that's okay. I'm going to show you an example right here. So if you look at this, again, I intentionally misaligned this, but if you look at these images, now I can just go to each of these and you see as you're acquiring an image, whether it is a cross beam, in this example, or a focused ion beam scanning electron microscope, FIB-SEM, or even other acquisition techniques, you may have a sample movement, you may have the beam movement, whatever it is. And if you're from astronomy, again, there is a lot of movement. So how do you align these so you can actually perform some image processing functions after aligning, after the alignment process? So there is always a need for image registration. Now, there are various types of these image registration, and the easiest one to think about is translation, right? In the example I just showed you, nothing happened. There is no rotation, only X and Y movement. So we can just recalculate the X and Y and bring the image back. You can also do the translation plus rotation. So there may be X and Y, but in addition to that, there may be rotation. So that's called rigid body registration. Now, in addition to that rotation, there may be scaling. So things may be stretching, things may be stretching, or compressing. So this is called scaled rotation, and affine is probably the most commonly applied type of registration, which includes translation, rotation, scaling, and also shearing, meaning you're stretching from one diagonally, from one side to the other. You're kind of skewing the image in a way. So that's affine, and bilinear is there is no nonlinear transformation. Like, for example, if you are imaging some 3D structure and you're compressing it, and the pores are elongating in one direction, and then things can move in very different directions. So bilinear can be a bit more complicated. Again, it's a nonlinear transformation. Now, the 2 or 3 libraries, and the first one I'm going to talk about is inspired by astronomers. And this is called image registration library. And to get this, you just do pip install image _ registration. And they have 2 different ways, like methods, Chisquare Shift and cross correlation shift. And again, if you're interested, you can read more about this. But Chisquare Shift is basically you have 2 images and they use DFT, the Fourier transform upscaling method, and they combine it with the chi-square to measure the errors between the fits. And cross correlation uses, as the name suggests, cross correlation and apparently a second order Taylor expansion. If you don't know what that means, that's fine. Using it is very simple. The other one that's actually a bit advanced is optical flow based image shift. And this is a part of scikit-image. You can also find it in OpenCV. This is it's basically the output of this when you apply it is a vector field. In simple English terms, at every pixel, you get a value of by how much it moved in X and Y. At every pixel, that's it. Okay, so you have to apply these pixel to pixel. The examples I showed you earlier, think of this as these are just 2D translations, right? So you get like the mean image is moved by these many pixels in X and these many in Y. Here you're actually getting it for every pixel. So which means by definition, this would be a much better approach. And both of these are sub-pixel, down to sub-pixel level. Okay, so your movement will be like 18.235 or something, And the other one is called PIstack Ridge. This is the one that I definitely recommend for microscopy applications. And if you're coming from image J, you may have already used this. Okay, so this is a Python or C++ porting of image J extension. And you may have used something called Turbo Ridge or Stack Ridge. And this is basically that algorithm in Python. And the best thing with this is it's an automatic alignment of like a stack of images, a movie, or you have a target image and a reference frame. And it also performs all types: translation, rigid body, scale, rotation, affine, and all of the things that we just mentioned. So if you are looking for one-stop solution, this may be it. Okay, so registering each frame. So there are many ways to register, right? So this allows you to do it many different ways. One of the ways is register each frame to the previous one. Okay, so 10th frame with the 9th and 11th frame with the 10th and so on. You can do register to the first image. You can say the first image is my reference and everything else just register to the first, which is okay, it works. But if the features change as you go along, then that can be a bit tricky. You can also do register to the mean image, mean of all these images. You can register to the mean of first 10 images, take a mean, and then register to that, okay? And calculate a moving average of 10 images. If you have 1,000 images, just take moving average of 10 images and register to this moving average and the first images and transform the original image, not a moving average. There are many ways of doing this. So what I'm gonna do right now is jump onto Spider and show you the first 3 ways, using optical flow, using chi-square and cross correlation, and then I'm going to save this PIstack Ridge for the next tutorial because this deserves its own tutorial. Okay, so let's jump into our Spider. As usual, I have a few lines of code. So for this, what I've done is, like I said, I intentionally misaligned some images, so that's what I'm going to use here. Okay. So first, I'm going to show only for one image for these 3 because I think I'm doing this only for informational purposes only, these 3. But then the PIstack Ridge, let's actually get a bit deeper, okay, in the next tutorial. Okay, so I have my reference image and the offset image I intentionally moved by minus 17 and 18 in Y and X, or 18 and minus 17, okay? So let's go ahead and run this. Okay, so both images are registered. So sorry, not registered, both. We actually imported both images now into Python. Let's actually apply, let me copy this part of the code. So I call this method 1, which is chi-squared shift. Okay, and it finds offset between image 1 and image 2. And I believe I opened up the library here. To install it, all you need to do is pip install image registration and then chi-square shift. So you can read more about it and just do a quick search for image registration package and you should be able to find this. Okay, so again, pip install image _ registration if you don't have it, and I bet you don't have this. Now, so here is how the implementation is. All these lines down here is just for plotting, so don't worry about it. And these 2 are the print statements. So here, what I'm doing is I am adding something called a noise factor, which is required for this chi-square shift. And once you apply this chi-square shift onto the image and the offset image, and with this noise and all these other parameters, you can extract 4 things: X offset, Y offset, okay? Error in X offset, error in Y offset. So let's just take the X and Y offsets, okay? I'm printing them here so we can compare with the real values. And okay, we just get X and Y offsets. How do we correct for it? So to correct for it, I'm just using the shift from SciPy ND image. Okay, so it shifts the image by whatever the parameters. So by how much do we shift? We shift it by X offset and Y offset. That's it. Okay, so let's go ahead and plot it. And you can see the output here, pixels shifted by 18.001 and minus 16.99. The real values are 18 and minus 17. So that's not bad. Very good. And if you look at the plots, not much you can tell from the plots. That's why I'm not, please don't pay attention to these plots at all. Okay, so this is using chi-square shift. Again, the values are 18.00 minus 16.99. Now let's use the second method, cross correlation, also coming from the same library, right? So the 2 are coming from this same library. Let's apply it here. Again, from image registration, I am importing chi-square shift, and my image is this offset image. I don't think I need to. Okay, that was a repetition, but anyway. So the way we are doing is, again, extracting 2 values, X offset and Y offset here, okay, by applying cross correlation shifts. And we are printing those values, and I'm using exactly the same function shift to kind of move my image back to its original position. So let's go ahead and print it and have a look at the shifted values. very similar, I should say, 18.001 minus 16.988. And I'll leave it to you to actually generate a synthetic image where you know the pixel movement down to subpixel and kind of compare these before you pick which one works for you the best. Okay, so now let me go ahead and let's actually delete all of this. So we have a clean slate here. And this one is very useful. Optical flow can be very, very useful. So let's go ahead and have a quick look at it. Oh, this method, actually, I squeezed in one more. Sorry about it. I squeezed in one more, but let me go ahead and explain this. In fact, scikit image itself has a function called register translation. Okay, this one gives you the shifted and the error values. So this is a built-in, the name suggests, translation or registration algorithm that does only translation. This is part of scikit image, so you may as well use this. And what it's outputting is an array for shifted. So I'm extracting the X shifted shift and Y shift, and I'm printing them out just like before, and I'm going to apply it just like before. Okay, so let's go ahead and run this to see what this one actually spits out. Okay, this one seems to be, well, they cut it off at the first decimal point, so I'm not sure. So they're rounding it off. So anyway, so the values here are 18.0 and negative 16.99. So any of these, they're all okay. They're all doing a great job. Yeah. So now let us actually go to the optical flow method. Again, this is available in both scikit image and also in OpenCV. I'm going to show you the scikit image implementation. You can also play with OpenCV implementation. I haven't used it, but you can do that. Okay, so again, because it's actually doing, calculating these vectors at every single pixel, it can be best for warped images, yeah, or even just for simple translation or rotation rigid body type of images. So how do we do that? Again, these lines are pretty much the same, right? I'm not changing anything here. And here now I'm from scikit image, I'm importing registration. As part of registration, you have optical flow. I believe this is only again available in scikit images version 0.16 or later. So I'm working on 0.17.2 scikit image. So if this doesn't work out, most of the time the chances are you have an older version of scikit image. Okay, please upgrade it. So from registration, I'm going to import optical flow TVL1. And the two inputs are, the first one is our reference image, second one is offset image. Okay, let us clean the slate. Let us go back to our variable explorer, clean everything, and start from scratch. Okay, let me run only these lines of code for now. And optical flow can be a bit slow. So when I run this, it'll take probably 5 to 10 seconds. Okay, so there you go. So up here, you can see my image and offset image, but let's actually look at the flow here. So the flow dimensions are 1104 by 1376, which is fine, the same dimensions as our image, but we have two values here, right? This is one for flow in X and one for flow in Y. So if I open this, you should see one for flow in X and one for flow in Y. So there you go, 0 and 1. Yeah, this is the first one, I believe, is for Y, right? 0, and the second one is for X. Okay, so this is the vector. So the first pixel moved in Y by negative 17.00, right? So we know that is true. It moved in Y by negative 17 something. The second pixel moved it by this much, so it's actually calculating. Don't even ask me why it's all not the same value. It's, but these are the values. So now what do we do? Okay, we have an optical flow. How do I apply that to my image? If it's only translation, what I would do is just take my flow in X, just take my flow in Y, and then get a mean of these values. That's exactly what I'm trying to do here. Flow in X, flow in Y, okay? Again, let's go ahead and run this in case, again, if you are new to Python, let's run this. So what we get in flow in X as 1104 by 1376, flow in Y as these many. So this is all the values for flow in X. Now I'm just taking the mean value. So if I run these lines, I should just get the average of all of those values, which hopefully would be close to 18 and -17, right? This is what, by how much we move the image. And then we can apply it just like before. Shift out of scipy.nd image, apply it to the offset image and shift it. Okay, so this is no fun though. This is no fun because why do all this exercise at every pixel and then take an average? You may as well use something else. Let's actually apply this flow vector to each pixel, right? At each pixel, I want to adjust it by certain amount. To do that, first we need to extract the pixel coordinates and then add this vector value in X and in Y. That's it. So how do we do that? First of all, let's actually look at my height and width of the image. Okay, image.shape. It tells us, okay, what is the height and width is, right? And then I'm going to create a mesh grid. Again, look at this. If you haven't used numpy.meshgrid, go ahead and look at the documentation. It returns the coordinate matrices from coordinate vectors. So by looking at this image, all I'm trying to do is get the value. Let's run this so you can see row coordinates right there. You see 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6. These are row coordinates. Now what else? Column coordinates. Let's open these column coordinates. Same thing. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Okay. It looks weird because the column looks like rows looks like column right now. I call them row and column because our image, I'm calling my height as the column and width as the rows, but you know, in here it looks at it a bit different. It looks at the other way around. So anyway, so experiment with this. So all it's creating is my top left pixel is 0, 0, and then 0, 1, 0, 2, and the next one is 1, 0, and so on. So that's the mesh grid it actually is creating. And then now I'm going to import something called warp. Okay, and for this I'm going to apply this warp onto my offset image, which is the second image that I'm trying to register. Okay, and offset by how much amount? Offset by whatever the row coordinates plus flow y. This is my y coordinate. Okay, and then offset this by in X by column coordinates plus flow in X. Again, I recommend you just going through this code and trying to digest it line by line. Okay, so we are extracting the row coordinates and column coordinates, and each coordinate we are moving it by certain amount in Y and certain amount in X. That's all. Okay, and then after everything, again, plotting probably doesn't make sense. Oh, I'm running the flow again, so this may be a bit slow, but I hope this makes the point here. So how to apply? Once you get the flow out, you're going to get the coordinates and you're going to move each pixel over there. I hope you found this tutorial to be useful. And again, in the next tutorial, let's cover how to use PIstack Ridge, which I bet is more interesting than this, but at least now you know how to do it at least 3 to 4 different ways. Thank you very much.